and which can affect the life of our components. So wear is of uh, crucial importance as far as reliability of mechanical engineering components are concerned. And along with it comes the question of friction. Uh, it's very easy to say that a knowledge of friction is essential from the point of view of energy consumption, but more than that, friction can be a very important factor in some very specific applications, like, say, for example, in sheet metal forming, where if you don't control friction, the quality of the finished product is going to affect um, your supply, I mean, your quality of production to a large extent. And then we should know that these two are not really independent. Friction and wear, they are closely related. So most of you who will be listening to this webinar, you are already used to this introduction, which I have just made some kind of a repetition just to get started in the proper sense. So we know that if we see what is there in the slide, then we know that I'm going to read what is in the slide, or I'm going to explain what is in the slide. Then basically we are interested in rubbing, in what happens when two interfaces they engage and slide against each other. So in a proper, in more technical terms, it is sliding, but in layman's terms, it is rubbing. And accordingly, you will have friction. And then where it happens at the interface between objects. So therefore, the nature of the interface between these two material bodies which are in contact, it's of that is of crucial importance and of concern as far as tribological scientists and researchers are concerned. Now, if you are talking of the nature of the surface, then we may broadly classify these two natures as to be belonging to the physical nature of the surface and the chemical nature of the surface. So we will soon see what all things can be classified as the physical nature of the surface, what all can be classified under chemical nature of surface. Then, so therefore we need to characterize, see if we can classify them into two broad categories as the physical nature of surface and chemical nature of surface, then we need to characterize them. We'll soon see why we need to categorize them. So therefore we would require some very special equipment and procedures for characterization. So what do you mean by characterization? What is implied by that? Means we are trying to kind of describe, but using some very limited, precise, compact information, the nature of what we are trying to express. Say, for example, if you are talking of roughness characterization, we are talking of some features of this roughness. We are trying to describe the surface features of surfaces using some very specific parameters. Thereby, we say that we have characterized this surface from the point of view of what we are trying to look at. Maybe I'll elaborate on this little later. Say, for example, somebody who is interested in the reflectivity of a surface, he would require some very specific number of parameters which can characterize the surface for his particular application. But those parameters which that particular physicist who is interested in studying the reflection properties of surfaces, he has selected as those properties which can characterize what he is trying to find. It may not be of interest, it may not be of use for an engineer who is interested in wear. He would require another set of parameters which can characterize the surface for his particular application that he is interested in. So therefore, we should, when we are trying to say of characterization, this characterization is not exhaustive in the sense we may adopt few parameters which can adequately describe what we want to include in our analysis, and they could be different in different scenarios. So next, why should we be interested in characterization of interfaces for tribology? So if we look at effect, what is given at the bottom, which is the tribological response, which are mainly in the form of coefficient of friction and information related to wear, like what is the wear rate, what is wear volume, what is the nature of the debris which are generated because of tribological interaction and sliding. So they are the tribological responses. So while doing tribological experiments, either as part of academic research or as part of our research and development investigations in an industry, we you as tribologists, we always, I mean, most more often than not, we come across very interesting dramatic changes in the responses, which kind of invokes some kind of curiosity as to explain why those dramatic changes in responses happen. Now those are the results, those are the effects. Now, as part of a scientific investigation, it is our duty to explain why those results have come. Now, if you want to establish if you want to find reasons, if you want to establish a rationale for those responses, then we should be able to link those effects or results with the primary causes which are resulting in those responses. So if you want to do that, then we need to establish that link between what we have found and what is actually, or what mechanisms are actually causing those particular responses that you, or the changes in responses that you have observed. So to establish them scientifically, because ours is basically an experimental science, we require experimental tools to look into those features of those interfaces. We have to look at them in the greatest detail that we can, and then we should identify few of them which can explain which can explain the results that we observe. So to do that, we need to link the responses with properties of the surfaces. So there is a cause and effect. So that is what I've shown in this slide. Observing those effects, which are tribological responses, we need to take them, or we need to explain those responses in terms of what are those things which are causing it. So to do that, we need to have some experimental tools or characterization methods which would help us relate the effect and cause. So those causes could be chemical changes in the lubricant that you have used, in the proper change in property of the surfaces, or some new synergistic effect which results because of a combined effect of, let's say, heating, because of pressure, because of chemical changes which happen to the lubricant due to the changes in the physical and chemical nature of the surfaces, etc. So this is one step ahead. I've shown two mating bodies, A and B, and so there is an interface between A and B. And so I've shown a small portion here, which is shown by this oval, which if we zoom it up, then maybe it would look like what is shown in this schematic figure, or what you would call as a cartoon, in which I have shown those two portions of those two solids, A and B, with their roughnesses exaggerated to a very large scale. So now you see this. So this could be the actual picture, what is happening when they are sliding against each other. When they are sliding against each other at such great contact pressures and temperatures, there could be all kinds of chemical reactions which gets triggered because of the contact pressure and because of this temperature. Now, when we are talking of this temperature, the bulk temperature of the interface that we may measure using some method, say using a thermocouple or using some other sensor which are fixed close to the interface, and then extrapolating using some mathematics to find out, to find out what would be the actual state of affairs which are exactly at the interface. It gives some bulk average temperature for the surface. In addition to that, actually we should know that because of this sliding, there could be a damage to those asperities which are at the micro level, which may get detached, and in the process there would be emission of electrons, there would be discharge in the form of photons, and then there could be very locally the temperature may rise to few hundreds of degrees Celsius. So all these things are going to incite cause new chemical reactions, and the lubricant that you have introduced into this interface, which you perhaps would have characterized before in terms of its molecular structure of the hydrocarbon and other things, etc., will now change to a large extent because of those reactions which are going to get triggered because of all kinds of interesting phenomena which occur at the interface because of these very high pressures and those extremely high temperatures which happen locally. And in addition to that, there could be reactions between this liquid or the fluid lubricant that you have introduced and between the metal. There could be, when they are sliding continuously, there could be generation of debris, means small wear particles which would get detached. So they themselves would score all kinds of new wear patterns, scoring, and things like that, which can also trigger new reactions. So there is a tribochemical reaction which happens at the interface. There is a tribology and there is a chemical action, which is actually resulting in that in a new layer which happens over a period of time. And the physical and chemical nature of that interfacial film after several slidings could be much different from the initial condition that you have started from. And therefore, we would experience or we would observe a different tribological response when time goes by. So we need to explain those changes which happen over a due course. So if you want to do that as an investigator, as a researcher, you will have to look at the new physical and chemical state of this interface, which is different from the parent interface before they started sliding. So now there are all kinds of interesting phenomena there. You observe a physical change in the surface, you observe a chemical change in the surface, which is part of this what we call as tribochemical film. So you need to characterize the new film which has got established there. So there are various methods of doing it. I've shown a small figure there where I've written chemical signature which can be explored through spectroscopy. So there are different spectroscopic methods which can investigate the chemical nature of those surfaces. To name few of them, they could be the X-ray photoelectron spectroscopy, which we would look into in some detail in the next part of what I'm going to discuss in this webinar. Then you can use infrared spectroscopy or FTIR, about which also we will spend some time today. In addition, these are the two most popular spectroscopic methods as far as investigation on tribochemical films are concerned. In addition to that, people use Raman spectroscopy also to identify some features which are not captured using these methods of XPS and FTIR, etc. Though I am not going to discuss upon Raman spectroscopy. So that is one thing. And now we need to look at what has happened to the physical state of this surface. So therefore, if roughness has changed, then we need to have some experimental tools or methods of investigating surfaces. So profilometry, whether you use a stylus, that means whether you use a pin, which most of you would be aware of when you do your experiments in BTech, mechanical engineering equipment lab, sorry, experimental labs in instrumentation methods, or perhaps in metrology, or even in your manufacturing labs, where we capture the features of roughness using a stylus or a pointer, which would move or slide along the surface and which would record these undulations, which you can use to calculate or evaluate different parameters of those random features in terms of the statistical average, the root mean square value, the skewness, kurtosis, etc. But if you want to do it at a more advanced level, then you should have some 3D profilometers, which are available in few institutes now. It was there. It's there for last at least 15 to, yeah, nearly about 15 years or 16 years in my professional career. So there are various methods of investigating surfaces using
Sir, it is okay, sir. Now you are visible. You can share, sir. Sir, you please unmute yourself, sir. Anirudhan, sir.
Hello, is it okay now?
Okay, sir. Now it is good, sir.
Okay, fine. So I'm sorry, my viewers. There is a frequent coming and going of internet connection.
Yeah.
I'm in my
It's
studio.
okay, sir.
In spite of that, if it keeps happening, just please bear with me.
It's okay, sir. No problem, sir.
Okay, thank you, Rajshekar. Let me
Thank
just.
you, sir. Thank you very much.
Okay, can you see the full screen now?
Yeah, it's good, sir. Full screen is visible now.
Okay, thank you, thank you, thank you. Fine. So we were here. So there is a, if you want to do more advanced investigations on the roughness, then you would require a 3D profilometer. So now I am coming to that. So first we said that we need to characterize the chemical nature of the film, which can be accomplished using HPS or FTIR or Raman spectroscopy or some other methods. We would definitely see about HPS and FTIR in today's webinar. Now then you need to look at what is happened to the physical state of the surface, of which the most obvious one has got to do with the roughness. So how are we going to characterize roughness, which has got to do with the uh, wear and friction. So how do we do that? We need to do using some methods which are related to profilometry. So we will discuss that. In addition to this, if you want to study about debris, what is happening to the nature of this debris and other things, then the most frequently used experimental tool is the microscope, and that too at a very low length scales microscope, which is done using electron microscopy, so which is called as SEM. So that is used for characterizing the debris. And also, if you want to see surface relief, means what happens to the damage on the surface because of sliding, because they are at very high contact pressures. So what happens to the surface? How do you correlate the features of those surfaces or those surface relief which result because of constant contact and rubbing? What happens to them, and how do you correlate those new features which you find from your from your microscopic investigations using SEM? So they are also crucial. So this list is by no means exhaustive. I have given few factors which should come under characterization, which is of interest for the tribologist. Okay, so now if you look at these surfaces, we can broadly characterize those features into two different categories or classes. One which is called as the physical nature of those surfaces, under which we may look at what happens to the hardness, which can be done through an indentation experiment or nano indentation experiment. Then we should look at roughness, which can be done through surface profilers, which we mentioned a couple of minutes back. Then you can look at surface relief, etc., which can be done through a secondary SEM image, scanning electron microscope image. On the other hand, if you want to look at the chemical nature of those interfaces, particularly if you want to see what has happened to the alloy distribution. So you may think like, what has alloy distribution has to got to do with this? Because let me just 1 minute on that. We will see one example where alloy distribution is also important. Is when metals they slide against each other under such high temperature, high contact pressure conditions. There could be transfer of material from one interface or from one medium, from one part of this interface to the other, which is akin to or which is similar to a new kind of an alloy which gets formed on one of those surfaces. So if you want to see the alloy distribution, which is called as the transition layer or the mixed layer which happens there, then if you want to study the alloy distribution, then we should use the SEM, but in a slightly different mode, which is called as backscattered SEM. So most of my viewers will be aware of it, but I'm just kind of repeating it for freshers. Then if you want to study tribochemistry, then we should use, if you are looking at the tribochemistry of the surfaces, then we should use XPS and FTIR. In addition to this, if you want to study tribochemistry more about what has happened to the fluid, you should use GCMS, which is mass spectroscopy method, or NMR methods, of which we are not going to discuss anymore about in this webinar. And then, of course, about species absorption also, like what happens when species absorb. Say, for example, if you want to study about hydrocarbon absorptions on surfaces, then you can use methods which are used for chemical characterization, especially that is related to FTIR. So these are the contents of this particular webinar. We have done surface characterization. We have talked about classification. Now we are going into the details of those characterization methods. We will be discussing about XPS, which is X-ray photoelectron spectroscopy. Then we will discuss about FTIR, Fourier transform infrared spectroscopy. We will discuss about characterization methods using scanning electron microscopy or SEM. And then we will definitely discuss about roughness characterization. So I'll discuss the basic science behind these characterization methods, what are the procedures for characterization using these methods, and then explain them using some of the results that I myself have found in collaboration with my collaborators, and using those results from our research publications and papers. So to begin with, I am going to talk about XPS, mainly because it is not so popular an equipment. While if you look at SEM, ideally I should have started from roughness or SEM. But to keep your interest very much alive, I thought I will start from XPS because it is not so much of a common equipment, and the results are also very interesting, which would give us some good fresh new ideas about how to characterize the chemical nature of surfaces, which is not so popular. So I'll start with the XPS one. So what you see on the screen there is some kind of an XPS machine. I'm not going into the details of that. This is how it would look. So the rough dimensions could be like the length of that cabinet could be something like 1.5 meters to 1.5 meters long by 1.5 meters high to something like 4 feet wide box. And then there is a computer console. So you have to load your specimen inside this and you have to get those valuable informations. Okay, so what happens is the shown here on the right hand side is a sample, and we are trying to investigate the chemical coordination of different elements which have got formed on this surface. So what you do is you subject this sample to irradiation by X-rays. When we say X-rays, they are very soft X-rays. In the sense, suppose if you want to study the hydrocarbon film formation on a surface, then obviously you don't want to destroy the surface. You don't want to change the chemical nature of the surface by modifying it because of the introduction of very hard, high energy X-rays. So you use very soft X-rays. We will see what those X-rays are. So when these surfaces are subjected to the soft X-rays, several things happen. One thing which I have not shown the complete details. Now, when they are excited or when they are exposed to these soft X-rays, electrons starts emanating from these surfaces, and they are called as photoelectrons. Now, inside this instrument, there are detectors which can measure the kinetic energy of those electrons which emanate from this surface. So this equipment is called as the X-ray photoelectron spectroscopy machine, or otherwise called as XPS. And it is also known as ESCA, which is electron spectroscopy for chemical analysis. Now, the energy of those ejected electrons from the surfaces, they are usually of this energy which is less than 1000 electron volts. Now, so if they manage to escape from this surface, then calculations have shown that these escape depths are from nearly 1 to 2 nanometers deep, because these are not so very high energy electrons. So therefore, since they are weak, they cannot emerge from the bulk. So those which emerge from the bulk, they would get absorbed in the matrix itself. They won't emerge out of it. They won't come out of it. So those which manage to come out of this, emerge out of this surface, they could be from depths which are not more than, let's say, 2 nanometers from the surface. Therefore, the information that we are going to get from these photoelectrons using this method are highly representative of those informations which are from the surface and not from the bulk. So that means they would provide excellent surface information because they emanate from very low depths, which you can say that they are almost from the surface because they are just 1 to 2 nanometers deep. So this is that equipment. Now what is it doing? You can use an HPS method to identify different chemical species or different chemical elements which are there on the surface. That is one thing. Another thing is you would get valuable information about the chemical bonding between those elements that you have identified from the surface. So first of all, let's see how does it identify different elements. So to see that, you see, I have shown a figure here which shows some kind of a schematic diagram which shows different electron levels in an atom, where I've started from the 1s orbital, which is called as the K shell, and then above which we have the L1 level, which is called as 2s orbital, then above which we will have the 2p, and then above which we will have the valence and conduction bands above this. Now, for very small atom elements, so you will see later why I am talking about very small atom elements now. When they are subjected to these X-rays, they possess enough energy to knock off electrons from these electron shells or orbitals. And what happens is let's look at what happens when this X-ray, it ejects an electron from the 1s orbital of the system. Now we can calculate the binding energy which is associated with this process by making a simple energy balance here. That means, see, I have written here, see, the kinetic energy of the electron which gets ejected from the system will be equal to the energy it receives in the form of X-ray, which is nothing but h nu, where nu is the frequency of the X-ray which is falling on this. So it receives an energy which is equal to h nu. And then let's say if EB is the binding energy that it has, means that is the amount of energy that you would require to eject it out. If that is represented as EB, that is our binding energy, then the kinetic energy of this ejected electron will be the difference between what it has received, which is equal to h nu, minus how much got spent, which is the binding energy. So that will be equal to h nu minus EB. Now there is another factor here which I have written here as minus 5, which is a correction factor, which is a matter of which happens there, or which occurs there, or which is presented there, which is a part of a definite machine as a calibration parameter. You may even neglect that. But the point to be noted is that the kinetic energy of the electron so ejected will be basically or mostly the difference between the energy it has received in the form of this X-ray, and the magnitude of that is equal to h nu. Out of this h nu, a portion EB, which is the binding energy, has got spent in detaching it from there. So that is EB. And then there is a small correction constant, which is a calibration parameter, which is minus 5. So from which we can calculate, so we can write this EB, binding energy, to be equal to, if we just rearrange that equation, we will get the binding energy EB will be equal to h nu minus E kind. That means the kinetic energy of this electron minus that constant term, which is phi, which is a calibration parameter which is specific to the equipment. Now our interest is in this EB. Now how can we get this EB? See, h nu is the energy of the X-ray which emanates from the source and which falls on the surface. So you know at what frequency that is happening. So that h nu parameter, it becomes known to you. Now, if there is some method of getting that kinetic energy of that ejected electron, then we have become successful in finding out what is the EB, the binding energy. So there are sensors or detectors which are fitted inside our equipment, which can measure the kinetic energy of those electrons which are ejected in this process. So you can calculate this binding energy EB as to be equal to h nu, because that is the input energy. You know at what frequency it is happening, so you can calculate what is h nu. If you can measure this E kinetic, that is the kinetic energy of this ejected electron, which is measured using suitable sensors and detectors. So the instrumentation or the censoring, the sensors part of this equipment is a very sophisticated one. That is what we should realize at this point, which can precisely measure precisely the kinetic energy of those ejected electrons. Then if you know this calibration constant phi also, which is applicable for your machine, then you can always compute what is the binding energy associated with that packet of electron which your detector has measured. So when people calculated those binding energies for different materials, which I have shown in the table which is below, for lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, etc., they found that the innermost electrons or the binding energy related to the 1s electrons. 1s electrons are the core electrons. They are the electrons which are the closest to the nucleus. Then the 1s binding energies of different elements, they are they are distinctly different. Say for example, if you look at the 1s binding energy for lithium, it is 50. If you are looking at the 1s binding energy for beryllium, it is 110. Similarly, it is 190 for boron, 280 for carbon, and etc. 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 So therefore, if you are suspecting nitrogen in your compound, let's say, when you subject it to X-ray photoelectron spectroscopy, and if you are sure that your X-ray is powerful enough to extract an electron from 1s orbital, and if you are getting a binding energy, because you are suspecting nitrogen, that is also important. You are trying to confirm whether it is nitrogen or not. Then if you are getting a binding energy which is either 400, which confirms elemental nitrogen, or a value which is close to 500, say for example 501.7, or let's say 398.2, then you can be fairly sure that there is nitrogen in your system, and then it is bonded. And the reason for you to infer that it is bonded, because the binding energy value that you are getting is not exactly equal to 400, but it is in a band which is plus minus some value within this 400, which denotes a bonding. We will see why it denotes bonding. So to the point to be noted from this slide is that the core shell binding energies of elements are distinctly different. They are clearly separated or well separated, which helps you to identify different elements on surfaces. If you examine their core shell electron energies, because say for example, if I am getting a value close to 110 and if I am suspecting beryllium, then I can say that yes, beryllium is definitely is present in the system. So this schematic explains how, what is this photoelectron, what is its kinetic energy, what is its binding energy, how we can identify different elements from information related to core shell binding energies of elements. So this slide, it shows an equipment of an X-ray photoelectron spectroscopy machine. So this shows a small diagram which is on the top left hand side of this slide, where I have shown an X-ray source. There is a sample, and then below that I have written soft X-rays, basically from magnesium K alpha radiation and aluminum K alpha radiation. So mostly these are the two popular sources which are used: magnesium K alpha X-ray source and an aluminum K alpha X-ray source, and their energies are, for magnesium it is close to 1253.6 electron volts, and for aluminum it is 1486.6 electron volts. So if you see this diagram, then there is an X-ray source which is exciting those electrons. They are accelerated into some kind of an hemispherical energy analyzer. We are not going to discuss about the instrumentation part much. And then there is a detector where the energies of different packets of electrons which should emanate from the surfaces are analyzed, and you will get that. Now, suppose if you are looking at carbon. So people have done enough investigation to find out that if you are looking at elemental carbon, that means it is in unbonded form. If it is pure carbon, then the carbon 1s electron energies for, sorry, the 1s electrons for carbon, they correspond to a binding energy of 285.0 electron volts. So if you are suspecting carbon in your surface, when you do an X-ray photoelectron spectroscopy, then if you are getting a value which is close to 285, either 285 or some value which is very close, in the close proximity or in the neighborhood of this value, you are more or less confirmed that there is carbon. And if those values are slightly different, then that is what I am going to explain next. So when it is pure carbon, carbon-carbon bonding, the 1s binding energy for carbon has been found by many investigators to be having a value of 285.0 electron volts. Whereas when carbon, it bonds with nitrogen, CN bonds. People have done investigations using XPS. They have synthesized those compounds, done enough number of experiments to confirm that when carbon it bonds with nitrogen, then the 1s electrons from such a system of carbon involving CN bond would belong to a binding energy of 286.0 electron volt. Similarly, when it is for COH coordination, bonding, or when it is for COC, then carbon 1s binding energy were found to be 286.5, and so many other values are also given. So the point to be noted, or the points to be noted, are as follows. When, if you are looking at carbon, when it is in unbonded form, that means when it is in element form, it is not in compound form, its binding energy has got one value. Now, when there is a bonding for carbon, then there is a shift in its binding energy from its parent value of 285 to those values like 286.5, 287.8, etc. So those shifts in binding energies are indicative of the chemical coordination between carbon and different other elements, which as an investigator you would suspect to be there on the surface. So you should have this database with you, so that when the binding energies that you have found from your experiment belongs to some particular value, then you can always use this database to find out what is the coordination between carbon and different materials that you would expect on the interface. So this database is available in lot many forms. Say for example, if you search the internet for something like LaSurface, lasurface.com, then it gives a very exhaustive list of different coordinations for each and every element in the periodic table, XPS binding energies it gives. So you have to do a search in that in a typical database like LaSurface to find out, to substantiate your hypothesis that carbon it enters into this kind of a bonding, it enters into this kind of a coordination with different other materials which you expect to be there at the interface. And then you have to establish the presence of those elements also. And with this information, you can combine all of them to say that, you see, carbon is getting bonded to nitrogen, or carbon has formed a bond with chlorine, because the carbon 1s binding energy from my XPS experiment for this tribological interface is giving a value of, let's say, 286.5 and things like that. So basically, why these binding energy shifts are happening? It is because, see, when it is in elemental form, that means when they are unbonded, then we know that we need to spend a definite amount of energy to kind of remove, to kind of knock off this electron from its core shell. It has got a very unique value. Now, when it's getting bonded, that means now this electron cloud surrounding this particular nucleus, they are disturbed. The electron cloud or the electron energy distribution surrounding the nucleus are all disturbed, because now it is under the action of a different atom and a different element. So now there is a bonding between them. Now, because there is a bonding, we know that when at the interface between these two elements, there is a, we cannot call it as an interface, but there is a new thing which gets formed there because of the bonding, which we represent using some very simple diagrams in our study of chemical bonding and things like that. So the point to be noted is this new formation is likely to affect the electron energy levels of the electron fields which are around each and every nucleus. And so now they changes to a new value because of this bonding. Now when you are trying to find this binding energy of a 1s electron, from, say, for example, if you are looking at carbon, when in unbounded form it has got a value of 285.0, but now let us say when it has got bonded with chlorine, now these electron energy levels are all different, they have got changed. So people have done experiments to form bonds with carbon and chlorine, and then when they found the carbon one has binding energy for carbon in this particular coordination for carbon and chlorine, they've confirmed that it is at a value of 286.5, which means it is different from its original parent value, original value of 285.0. It is because of bonding, these electron energy levels are perturbed or disturbed, and then they changes to a new value. And because these new values are called as shifts, you can use this information on shifts in binding energies to correlate with the kind of bonding which you have to use your information related to chemistry, chemical bonding, and then your understanding related to their physics and chemistry. So you can use this equipment to identify elements. You can identify their bonding with some prior information related to the different kind of elements that you would expect at the interface. So that is important. You have to reduce the number of those elements which you are expecting at the interface. Say, for example, if you are doing an experiment using steel using an hydrocarbon oil, obviously you won't expect the presence of, let's say, uranium there. You would expect iron, you would expect carbon, you would expect some amount of silicon, you would expect something else also. If there is an additive, let's say lead is there in your lubricant, you may expect lead also there. So that set is finite, it's very small. Now your idea is to confirm the presence of those materials on the interface by using XPS, as I said, and then you can you can form some kind of an idea, though it cannot be complete, because one characterization alone cannot give you the complete details of the chemical coordination, but it will give you some basic information about the coordination related to those different elements which you have included in your set using this particular method. So to do that, I am just repeating it. You would require a very large database so that you can search in them to find out the kind of coordination that you are expecting between carbon and nitrogen, or perhaps between carbon and oxygen, carbon and iron, and things like that. They are available free of cost in lot many sites. The most popular among them being La Surface, lasurface.com. You can just Google and enter into their website and get it. Now, if you look at what is happening to these binding energies, then I am going one step deeper into this. Then these binding energies, let's say, for example, if you see this slide, on the top I have shown how the binding energies for nitrogen would change depending upon the oxidation state of nitrogen. So I've shown three different compounds there: NH2, NO2, NO3. So there is an NH2 coordination, there is an NO2 coordination, there is an NO3 coordination, in which if you look at NH2, then the oxidation state for nitrogen is -2, while it is +4 in NO2 and it is +6 in NO3. If you see the binding energy for nitrogen in these two environments, then we will see that the binding energy, the core shell binding energy for nitrogen is the largest when it is for NO3, when it is at an oxidation state of +6, as compared to what you would find it for NO2, where the oxidation state for nitrogen is 4. It is intuitively correct, because so many number of electrons are contributed by nitrogen now. So therefore, what happens is those core shell binding energies are now not so much in the influence of those valence electrons, and so therefore they would feel a more positive, sorry, those core shell electrons would feel a more attraction now towards the nucleus. Why? Because they are feeling a less attraction from those valence electrons, because those valence electrons are now more or less contributing to the bond which is with its neighbor. So therefore, though core binding energies would experience a slight increase now. Core shell electrons would experience a slightly more. They would feel as if they are pulled towards the nucleus with a slightly more energy. So therefore, they would experience a higher binding energy. Now, for a given oxidation number, by the same argument, for a for a given oxidation number, the binding energies would change according to the electronegativity of the element which is trying to bond with this. So I've shown a figure which is below, which is similar to the one which we have shown above, where we are trying to look at iron, where iron is bonding with bromine, is bonding with chlorine and fluorine, FeBr3, FeCl3, FeF3. The oxidation stage for iron are same in all these cases, but the electronegativity for fluorine is higher than that of chlorine, and that for chlorine is higher than that for bromine, which means these valence electrons are now pulled by a greater and greater affinity by those neighboring atoms. So by the same logic or by the same argument that we explained for the oxidation state case, the the core shell electrons would now experience a much lesser force from those valence electrons, and therefore they would feel a slightly more pull towards the nucleus, and therefore their binding energies would increase. We can use all this information to extract information about a chemical bond. So this is a slide which shows different binding energy and binding energy shifts for an element like gold. So the website last surface, which I mentioned a little while ago, would give information which is similar to what I have shown here, though it doesn't show in the form of this graph. It would simply give those values. So for example, if you look at gold, it shows a binding energy of 84 for 4f7 by 2. We will see what is that 4f7 by 2. Whereas when gold is getting bonded with stannum, tin, Sn, then the 4 of electron binding energy for gold, it shows a shift. It is almost like 84.5. When it is AuSn4, its value shifts to 85, and then you get a distribution. So this kind of information is available in literature, or as I said, it's available in different websites also. Now coming back to that problem which I raised just now, it is not showing 1s binding energy for gold. It is showing 4f binding energy for gold. It is not talking of 1s binding energy. The reason being that, see, gold is not a light element. It is not a small atom. It is a large atom. Now when you are using these soft X-rays like aluminum K alpha and magnesium K alpha, the energy of those X-rays are not penetrant enough to knock off a 1s electron from its core. It cannot penetrate so deep. So it would be limited to some level, which for gold it is 4f. So it is showing 4f. In fact, we will experience the same thing for iron, because these X-rays cannot penetrate beyond 2p levels for iron. Now it has its own consequences. So we will see that in the next one. This gives rise to a very interesting result, which is called as spin orbit coupling. So as tribologists, you may not require the science behind all these, but tomorrow when you subject your sample to a chemistry division for investigation, and then let's say if you want that particular analyst or technician to give you X-ray XPS information related to iron, so he may obviously ask you which information do you want, whether you want it from Fe2P half, or whether you would require it related to Fe2P 3 by 2. So therefore we should know what he means by that. What is the difference between Fe2P half and what is the difference between Fe2P 3 by 2? So that, because now there are two values, Fe2P half and there is an Fe2P 3 by 2. So there are twin values, or there are two values, or there are two, this is called as a doublet. So this phenomenon, or the reason why this is happening, is due to a phenomenon which is called as spin orbit coupling. Because of spin orbit, so I will explain what is spin orbit coupling. Because of spin orbit coupling, the energy related to few electrons within an orbital, you can have two distinct values. This doesn't happen for an electron which is emanating from s orbital. If you remember, we said that the carbon oneness binding energy, sorry, the binding energy of the core shell binding energy of a oneness electron is, for carbon it is something like 280. It is a single fixed unique value. There are no two different values there. It is because those electrons, they emanate from an s orbital. Now if it doesn't belong to an s orbital, if it belongs to orbitals like P, D, F, etc. Like we saw the case of we saw the case of gold, where it was from F orbital. Similarly, in another case, it could be from D. In the case of iron, it can penetrate only up to P, so it emanates from P. So I have shown a figure here, which is in the form of a cartoon here. I have shown the 1s orbital, I have shown the 2s orbital, I have shown the 2p orbital. So let's say if we are looking a case like iron. So therefore, these soft X-rays, they are capable of penetrating only up to, let's say, 2p. And if it knocks off one electron from the 2p shell, so that is what I have shown in the left. A soft X-ray capable of knocking a 2p electron in iron, it is unable to knock the 1s or even 2s. That is what we should know that. Now, since it is from the p subshell, the quantum number corresponding to that is represented by this L value, the orbital quantum number, which is L. And for p subshell, that L value is 1. We should know that if it was a S subshell, the value of that L would have been equal to 0. Now, since it is from P, the orbital quantum number corresponding to that will be equal to 1. L is equal to 1. Now, the total momentum associated with the electron, whether it is from S or whether it is from P or D or F, it has got two contributions. One, because of its orbital number, and also from its spin, which is denoted by S. Now, if L is a value which is different from 0, like what we find here, in this case we found that L is equal to 1. So if L is equal to 1, then this S is the spin quantum number, which can be either plus half or minus half. So if L is equal to 1, then we would get this total momentum to be equal to 1 plus half and also 1 minus half, because this S will have two values, spin, plus half and minus half. So if L is equal to 1, then the total momentum is not unique. There are two different values for the total momentum. Either it can be 1 plus half or it can be 1 minus half, or in other words, it is either 3 by 2 or 1 by 2, which means there are double or two momentums, or in other words, there are two energies associated with them. And so therefore, few of those electrons which are getting emanated, which are ejected from 2p, will have an energy corresponding to this 3 by 2. And few electrons which are ejected from that same orbital can have a value corresponding to this half, which means they are because they possess two different values for their momentum, their energies can also be different, and therefore you will experience two different peaks which are close by, one corresponding to the 1 by 2 value and the other one which is corresponding to the 3 by 2 value, which are designated as Fe2p, means iron, and then 2p orbital, but corresponding to minus half spin. So that is Fe2p half, and the other one is again Fe means iron, 2p means from 2p orbital, and the other one corresponding to a spin of plus half, which is giving a value of that L plus S value of 3 by 2, whereas it is giving a value of 1 by 2. So I made a point that when it is emanating from an S orbital, means when L is equal to 0. Let's see what is happening when L is equal to 0. When L is equal to 0, the total momentum will be equal to 0 plus S. So you will get 0 plus half, which is equal to half, and 0 minus half, the magnitude is still 1 by 2. So therefore, in that case, there won't be two different values. There is one unique value. So you will get only one peak corresponding to an electron, corresponding to the binding energy for an electron which is emanating from an s orbital. If it is not from s, it could be from P, D, F, etc. Then their L values are not zeros. They are all different from zeros. Like L is equal to 1, L is equal to 2, L is equal to 3, etc. Then you will have two different values for the total momentum. Like when L is equal to 1, we found that is equal to 1 plus half and 1 minus half, etc. Similarly, when L is equal to 2, you will have 2 plus half and 2 minus half. In all these cases, it gives rise to two different values of energy, and therefore, from your XPS data, you will observe a doublet. This is called as spin orbit doublet. They are called as spin orbit doublet, and this phenomenon is called as spin orbit coupling. So to contrast this Fe, I have shown the carbon 1s peak, which is on the top left corner of this slide, which is from carbon. And then the X-ray was penetrant enough to knock out a 1s electron from this. So therefore, for this L is equal to 0. So you will get a single value, unique value for your momentum and a unique value for your energy. And therefore, in your XPS peak, you will not see two different values for those binding energies. You will see only one unique value, which is what I have shown here. Whereas for iron, you will see a doublet. So ultimately, so there is one more question now. So which one you should select for your characterization? You can use, you can use either of those. You can either use information related to Fe2P half, or you may choose Fe2P 3 by 2. It is up to you which choice you want to make. It depends on, say, for example, if you want to study coordination of iron with something else, say, for example, you want to study coordination of iron with carbon, let's say. If the binding energy values quoted in your database, they are referring to Fe2P 3 by 2 values, then obviously you will have to look into Fe2P 3 by 2 binding energy shift and their values. Whereas if the database that you have or that you are referring to, it refers to Fe2P half values, then obviously you should be looking into the other peak which is related to Fe2P half value. So the choice is yours, but then it is dictated by those considerations. Okay. Now I am going to show you a result which we have found using XPS, which got published in this journal, Colloids and Surfaces A, which was part of a research for my PhD, which I did along with my professors, Professor Satish Vasu Kailas, who is very popular and who delivered a lecture in today morning's webinar, and then late Professor S.K. Biswas, who was a professor for both of us. Professor Satish was my professor, and then Professor Biswas was our senior professor, under whom Professor Satish Vasu Kailas did his PhD. So I had the opportunity to be associated with great men like Professor Biswas and Professor Satish, and we had done XPS to investigate about the chemical formation which happens when we do tribological experiments using oil in water emulsions, the applications being in the area of metal cutting tribology. So this shows on top, it shows the carbon 1s spectra corresponding to two different tribochemical films. The one which is on the left, it shows the carbon 1s part of the XPS data when there is starvation. And the one which is on the right, it shows the carbon 1s data when there is no starvation, means it is well lubricated. Now, if you see this difference, because we should know that this is it is an oil in water emulsion, you can see that what is conspicuous in the case when it is well lubricated is the presence of a C double bonded O peak, which is on the right hand side. That means the presence of a carbon double bonded O formation in the case of a well lubricated film, which is evident from our XPS data, while it is not so when there is starvation, because it shows very poor formation of C double bonded O structures there. Now, I have superposed these two XPS data below and shown in color just to make it evident that what is actually making this film more lubricious, what is making this film having less coefficient of friction is the presence of this metal carboxylate which gets formed, and that is something that we have detected from our XPS data. The actual reason for that is this C double bonded O formation, it is from a metal carboxylate. We should know that this is a tribological application involving a metal, which in this case was iron. Then there was a hydrocarbon because we were using oil in water emulsion, and there was water. So because of this chemical reaction between iron, the hydrocarbon, and this water, under suitable condition, these metal carboxylates are formed because of tribochemical reactions, and the structure of those metal carboxylates are similar to that of grease. They are greasy compounds. They are highly lubricious, soft compounds which would allow easy slip or cleavage or shear, providing a very lubricious film. So this is from our XPS data. And then this is the oxygen oneness part of that spectrum from those two films. Previously, we looked at the film for carbon information. Now we are looking at the oxygen information from those same films, under starvation and without starvation. Now, what is conspicuous here for the oxygen information is that when there is no starvation, or in other words, when it is more lubricious, exhibiting very low coefficient of friction, there is a presence of chemisorbed oxygen which gets formed under no starvation, which means it is at very low sliding speeds. If you see this, no starvation is at a very low sliding speeds, which is almost 1 decade slower sliding speed as compared to the other one. It promotes the formation of a chemisorbed oxygen. Now, the formation or the presence of chemisorbed oxygen, it has been investigated by many investigators and researchers and found to be a very crucial element in the formation of lubricious tribofilms employing this kind of lubricants. So this is about XPS. So now I'm going to discuss about the roughness characterization part. So I am done with my XPS. I am going to talk about roughness. I will talk about FTIR at the end. Next is about roughness. So we have finished one part, which is XPS. Now I am going to look at how is it possible to characterize friction. So characterize roughness fact features for friction. So as I said, we used optical, or this is one method of looking at the surfaces. You can use optical profilometers. So this gives an optical profilometry image, 3D optical profilometry image from a surface, which is rough as compared to the next slide, which is showing a more smooth one and exhibiting less friction. So which means our intention is to characterize this surface or functional characterization of these surfaces from friction point of view. So when these surfaces, when they come into contact and when they are sliding against each other, when they form a tribo pair, if there is no intentionally added fluid or lubricant which is added at the interface, if there is no presence of such things, then we would expect these metals, if they are two different metals, let's say, then they should come into contact. So there is adhesion. And then because of this roughness, when they are trying to slide against each other, the resistance to sliding, which we perceive and measure as friction, will have contributions both from stiction or adhesion and also due to ploughing. Now this ploughing is due to the interlocking of these asperities, and that is related to our roughness, while this adhesion is not so dependent on our roughness. So therefore, if you want to look at ploughing alone, ploughing in the sense those resistances which are imparted due to asperity interlocking, because when one material or one surface is trying to plough against the other, there is no stiction. There is contribution from this resistance to sliding because of asperity interlocking. That is what we mean by ploughing. Then in that case, we would ideally want this adhesion to be zero. We should perform experiments when the friction is caused only due to ploughing. There should not be any contribution due to adhesion. Then the friction registered in that experiment will be related to resistance due to ploughing, or in other words, resistance due to asperity interlocking, or in other words, resistance due to roughness on surface features alone. So one way of accomplishing this, that is reducing adhesion to a large extent, reducing it to a value of close to zero, is to do it under lubricated condition, because in lubricated condition the resistance to traction, the resistance to sliding, which is measured as the friction, which is mu. So mu under lubricated condition will be more or less close to the resistance due to ploughing alone, because the resistance due to adhesion will be close to zero. It is not zero, but it will be much, much less than what will be caused due to ploughing, or in other words, that is contributed due to asperity interactions, or in other words, which is close to the roughness effect. So therefore, we have to do experiments under lubricated conditions if we want to isolate ploughing to a large extent and study it in some kind of an isolation. So we did experiments using 4 different materials. When we did scratch tests on steel surfaces made of EN8 flats, we used 4 different materials which are shown there in this new slide. We made pins of aluminum magnesium pin, copper pin, super purity aluminum pin, and lead pin. So that means we used 4 different combinations of materials. Then we changed the surface features of this hard substrate, or this bottom material of the surface, which is EN8 flat surface. So these experiments were done by a gentleman by name Pradhi Lanzi Menezes, who is in USA now. Is a professor in some university. I think he's in University of Wisconsin. I was there also, part of it, trying to investigate. He was more or less into the material science and metallurgy aspect of sliding, whereas I was more or less concerned about the surface roughness part of doing this. But the data which I had used were basically from from Pradeep Lancy's experiment. So Lancy, what he did was he generated different surface features for these flat surfaces. So we will see that he developed surfaces which belong to 2 different categories. One which was called as surfaces with lay, and the other one were without lay. That means he differentiated his surfaces into 2 different categories. One which exhibited some kind of a waviness, which were called as surfaces possessing lay, and those surfaces which did not have any waviness, which were random, they were called as surfaces without lay and random. So, and then we did experiments, or rather Lancy did those experiments. I was the man who investigated the surface features and correlated those surface features with his experiments. So he made something like 19 different surfaces using all these combinations. So for example, if you are trying to look at an experiment involving an EN8 flat surface with one particular type of pin, let us say if you are looking at copper pin, he generated 19 different kinds of surface features for this EN8 flat surfaces. And then the same pin was made to slide against these 19 different surface features. And in each time, and of course, they are all under lubricated condition. And then he recorded 19 different friction values for each of these experiments, because there are 19 different surfaces now. So you would get 19 different values. And those experiments were repeated. We know why, because they are based to satisfy some statistical requirement. Those experiments were repeated 3 or 4 times, and their average values of coefficient of friction were taken. So he performed 19 tests under lubricated condition. And then we wanted to see from the experimental data from those features which were captured using the profilometer, we wanted to correlate those features of topography with those values of coefficient of friction that he could register from his sliding experiment. So that was the challenge that was given to me. Can you look at those surfaces, extract features from those 19 different surfaces, correlate them with the friction that were found for those 19 different tests, and come up with some magic parameter which can explain this friction in terms of those features that are found from the roughness parameters obtained from the profilometer. So there are n number of roughness descriptors, statistical parameters like RA value, RQ value, that means the root mean square value, the standard deviation value, sorry, the root mean square value, the centerline average, skewness, kurtosis, the maximum peak value, etc., etc., etc. There are those conventional statistical parameters or statistical measures which are used to evaluate the roughness features. Now, what we did was we we did those experiments, and then we found the correlation coefficient between those friction values and these statistical parameters, and then we made a table like this. So this table is a huge jungle. Say for example, if you take the RA value for experiment with aluminum magnesium pin, the correlation coefficient that we found between the friction experiment while using aluminum magnesium pin and the centerline value RA is only 0.32. While instead of using the RA value for these experiments, if you use the root mean square value, then the value of that correlation coefficient was only 0.21 for this particular experiment, and so on and so forth. So what, I'm not going to read all the contents or all the elements in this matrix, but the point to be noted is that the correlation coefficient between all these usually used values of roughness descriptors, the correlation coefficient between the descriptors of the roughness of the surfaces and the observed friction values were very poor. In some cases, they are as low as something like 0.2. And in some cases, when we were fortunate, we got something like 0.8 and 0.7, but it was not guaranteed, which means that these so-called descriptors are not completely sufficient enough to describe the roughness features of those surfaces that we used, which can explain the friction, or in other words, explain the roughness features which are contributing to ploughing, or the resistance due to interlocking and causing resistance in sliding motion. So these descriptors of these surface features are found to be ineffective because their correlation coefficients are very less. They are not trying to explain what is happening in reality when these experiments are supposed to simulate the asperity interlocking. You get a value of friction, but then these descriptors are not powerful enough and sufficient enough to explain them in full details. So that is the meaning of this table. So we thought, like, if you just look at the power spectrum from these surfaces, then I have shown two different power spectra, one which belongs to a so-called rough surface, and I have shown the power spectrum of another surface which was classified as smooth, as we saw in the beginning on some 3-4 slides previous to this. We saw a rough surface, we saw a smooth surface. So obviously we would expect friction to be high for the rough one and friction to be low for the smoother one. Now when we observe the power spectra from those surfaces, then we found something which is very striking. You see, there is a large demarcation, there's a large difference about the information this power spectrum from this rough surface is trying to give as compared to the information related to power spectrum from a smoother surface. So therefore we thought, why don't we use information related to this power spectra to to deduce something out from them, to formulate perhaps one parameter or more than one parameter or more than one parameters which can explain those friction values. Now, how do we say that they would explain? Because they should give a more value for the correlation between the features of what we are trying to include in our parameter and those friction values. The information that we got, that idea we got by looking at this power spectrum, because as you can see, there is a clear difference between the power spectrum which corresponds or which belongs to a rough surface and the other one which is belonging to a smoother surface. Professor Bobji is going to give a very detailed webinar, seminar on this in this series of webinars related to surface characterization. So he would discuss more details about all these things. It has got a connection with fractal geometry and things like that. And Professor is an expert in those ideas. So he will go into the details of those things. I'm not going to do it. But I would like to tell you that the surface which is on the right hand side is more close to being called as a fractal, while the other one which is on the left is less likely to be called so. Anyway, that is not our concern. What we did was, we found two parameters belonging to this power spectrum. One which is a measure of the area under this curve, which is a measure of the RQ value, the root mean square value. So we use this RQ value of this surface. And then if you see this power spectrum, which is an idea which actually belong to electrical signal and communication engineering science, this power spectrum. So on the x-axis, you will find this frequency. Now, if you see this between the rough and the smooth surfaces, if you see this, you see, if you find the centroid of this system, that means some mean frequency which is belonging to this surface and a mean frequency which is belonging to the surface which is smooth. When the surfaces are rough, we saw that the centroidal frequency or the mean frequency associated with this capture of this power spectrum, it moves further towards the right, whereas in this case it moves to the left. So this has got a connection with the frequency of packing of different levels of roughness features on this surface. I'm not going to describe those features in this particular webinar, but I will show you a paper where we have published these results. I suggest, if you are interested, you please go refer to that paper where these features are explained in detail. I cannot find enough time to do it now. And in case if you have any queries or doubts or something else, you please come back to me. But the point to be noted is, you can use features of power spectrum to clearly differentiate between rough and smooth surfaces. We use two different parameters from this power spectrum. One which is the root mean square value. So you may ask me, what is the connection between root mean square value and the power spectrum? The area under this power spectrum is a measure of this RQ value. So we can use RQ value because there is a more common descriptor. And we used another parameter which is related to the frequency of this packing, which we found as the centroidal frequency, or some kind of a representative frequency, which is a mean frequency or a centroidal frequency belonging to this spectrum. When you compare that mean frequency in these two cases, you will see that that mean frequency, it is more towards the right for the rougher one, while in this case it is more closer to the left hand one because it is falling down. There is hardly any contribution from what is happening on the right because it is falling off. So we use those two parameters, RQ and the mean frequency, and these results are published in this paper, a parameter characterizing ploughing nature of surfaces close to Gaussian, which was authored by me and my senior Professor Pradeep Lansi Meneses, whom I mentioned, and our Professor Satish Kajlas. And when we plotted this hybrid parameter, which is a combination of our RQ value and this frequency parameter, you can see that they would become dimensionless. So when we plot our coefficient of friction value against this newly formulated roughness parameter. Mind you, this is a very novel parameter. Nobody had done this before. I shouldn't say this. This is not an advertisement for what I have done, but still, this idea was new. This parameter is also new. Then when we plotted these experimental values of friction against that parameter that we formulated, then you see when you plot this graph, we see that it's almost falling in line, which has got a correlation coefficient of 0.93 for this experiment, which means now this descriptive hybrid parameter of the surface is largely able to explain the changes in friction for these different surfaces. A small value of this parameter, which is at this point, it corresponds to a low value of friction due to ploughing, friction due to asperity, interlocking, and roughness. Whereas a large value of this parameter is indicative of high value of friction. So this is for this experiment for aluminum magnesium alloy. Shown below is the experiments under lubricated condition for while using copper pins. In the next slide, you see that this is the variation of coefficient of friction under lubricated condition when you are using another different material for aluminum. And similarly, you get it for another different material for lead and things like that. There are differences also. We have explained all these things in that paper. Now, these correlation coefficients are quite high. They are of the values of 0.93, 0.92, etc., which means nearly about square of these values. That is 0.9 means a correlation coefficient of 0.9 means nearly about 81% of variation in coefficient of friction can be largely explained in terms of RQ, which is a descriptive of the peak values of distribution, and the other parameter which is indicative of the frequency of packing of different asperities. And so we find a very large amount of coefficient of friction. We did correlate this with experiments under dry condition also, in which case it doesn't follow a line, it would follow a curve. We have explained why it follows a curve and why this pattern is followed based on another parameter which is called plasticity index, which comes into play during rubbing under dry conditions. So the bottom figure, which doesn't show a line, which shows a curve, is actually for dry experiments, and we have explained this also in our paper. Okay. Next is, so I will take some 10-15 minutes more because we started late by 10 minutes. I've crossed my limit because it is 3:30 plus now. But I hope this will be useful for you. So I'll take another 10-20 minutes to complete this webinar. Please bear with me. So now I have finished my description about XPS, chemical characterization using X-ray photoelectron spectroscopy. Then we discussed about characterizing the roughness from the point of friction. So that was from the point of friction alone, nothing else. Just about ploughing nature of surfaces resulting in friction, that's all. Now I'm going to another popular method which tribologists use, which is called as scanning electron microscopy, which perhaps all of you may be knowing. I'm doing it for completeness sake. So we see features at very large magnifications using a microscope. So I have shown some figures there which are taken from another source. It shows magnifications under 75x, 150x, 450x, 1000x, 2000x, etc. Now what is obvious is when you are doing it under a microscope like SEM, the magnification it improves without loss in resolution. That is what is of importance. That means it is getting magnified, but at the same time, the resolution is intact. So how does it work? The schematic of this experimental facility is like this. It has got an electron source. In most cases, it ejects electrons because of thermionic emission, which are focused onto your point of interest, which are focused because they are electrons. They can be focused and defocused using electromagnetic coils. So they are focused onto your surface. And when they reach a surface, that means when they interact with the surface, it results in all kinds of interesting ejections. Like it gives rise to different groups of electrons. In fact, it gives rise to emission of X-rays also. Correct. Now, if you see these electrons which are emanating from this surface because of the effect of the incident electron beam onto the surface, if you collect those electrons which emerge out of this because of the incident electron beam, see in this case it is incident electron beam, whereas in the case of XPS, which we discussed half an hour back, it was X-ray, but now it is a beam of incident electrons. So they would interact with this matter and in turn would eject electrons. So if we collect those electrons in using a detector which is similar to what we mentioned about in the case of XPS, then the energy distribution of these electrons because of the impinging incident electron beam, these emerging electrons from the surface, if you plot the energy distribution of them, then this is how their energy distribution would look like. I'm not going into the details of it. It shows a distribution, but then we should know that there are two different packets. One packet, which is on the left, which is of low energy values, whose magnitude is close to 3 electron volts. And the other one, which is on the right, which is of the order of 50 electron volts, which is towards the right. So basically, there are two different packets. Of course, they are not two discrete different packets, but mostly we can say that they belong to two different classes. One which is centered around 3 electron volt, which are low energy, as compared to the other packet, which is at a high energy and has got a value of nearly about 50 electron volts. So therefore, now if we have two different detectors, so that is what I've written at the bottom of this slide. So there are two packets basically. One packet whose electron levels are less than 10 eV, mostly centered around 3 eV, which is a low energy electron packet, which we call as secondary electrons. And there is a high energy packet whose energies are of the order of 50 eV. We call them as backscattered electrons. So if we have two different detectors, one which operates in this bandwidth something like close to 0 to 10 eV, then you would be capturing the secondary electrons. If you have another sensor which operates in the range of, let's say, 50 eV, they would capture the second packet. We call the second packet the backscattered electrons. So what are those backscattered electrons and secondary electrons is what is explained in this particular slide. So backscattered electrons are electrons scattered back from the matrix, and those amounts of backscatter, so that means they impinge and then they deflect back. So the amount of deflection back because of impulse, because now they go and hit against the target and then they are now reflected back. Now this interaction, it would depend on what is the target nucleus, the target nucleus. So therefore, those electrons are called as backscattered because they are getting backscattered when they go and hit against a species or an atom. So electrons scattered back from the matrix, and the amount of backscatter depends on the material, whether it is carbon or whether it is uranium. You will get two different energies for those backscattered values. Now, while the secondary, they are due to the interaction of the primary electron beam with loosely bound outer shell electrons. That is, so I'll show it in the next slide. In fact, two slides here. So this slide, it shows a simulation of an electron beam which is falling down and then its interaction with matter. So this incident beam or incident electrons, it is getting spread inside this matrix, and then in the process it would get scattered back. So we see a backscattered scheme here. And in addition, because of its interaction with the elements which are inside this matrix, when they are bombarded against those elements or electron fields which are belonging to the elements in this matrix, few electrons from them would get ejected from those. So they are called as backscattered electrons. So coming back to this, that's what I've written here. due to interaction of the primary electron beam with loosely bound outer shell electrons belonging to the matrix material. I have not written it there. They are of low energy. Since they are of low energy, those secondary electrons which manage to escape from this matrix should definitely be from very low depths from the surface, because they are of very low energy. They cannot be belonging to the deep from the depth, because if they were emerging from the depth, they would have got absorbed, as we discussed in the case of our XPS case. So therefore, these secondary electrons, since they should be from very low depths, they would carry useful information related to what is at the surface. And as surface scientists, as tribologists, we would find information from them to be very, very useful. Now, if you see this, so this is this is how the yield from a backscattered scheme would depend on the atomic number of the species material. So you see that the backscattered yield, it would change according to different species, different target materials, while the secondary electron stream, it is not so much depend on the atomic species which is in question, though there is a dependence, but that dependence is weak. So therefore, you can use your backscattered packet to differentiate between different atomic numbers. Or in other words, you can use your information from your backscattered energy to differentiate between two different materials, A and B. Their distribution, at least on the surface. Where do you find A? Where do you find B? We will see that, how we do that. Whereas if you see the secondary yield, that means yield of the, or the flux of the secondary electrons which are getting emanated from the surface, then they are found to be sensitive to the surface undulations or changes in slopes of the surface. So if you plot the secondary yield against the angle of tilt from the surface, you will see that the secondary yield is largely dependent on angles of tilts or surface relief, while the backscattered is not so dependent. So therefore, you can use the secondary electron information to differentiate between differences in surface reliefs, that means differences in distribution on the surfaces, their geometrical differences in their relief. So this picture, it shows a backscat. It is the same base plate. I mean, the base information is the same, but it is the image when we use two different informations. The top one is when we are using the backscattered electrons, and the bottom one, it shows the same spot when we are using the secondary image. So when we are using the backscattered image, it shows areas corresponding to different distribution of species. For example, you can see the zone where it is fairly homogeneous and belonging to one different species, whereas you see different spots perhaps belonging to another species. While coming to the bottom half of this image, which is from a secondary image, that information is lost. Instead, it is showing the surface relief or the undulations and peaks on that very same surface. So you can use backscattered image to differentiate between areas belonging to different species on your tribological interface. Whereas if you are interested in finding the in relief, that means distribution of surface features which would get reflected in terms of peaks and valleys on your surface, then it is advisable that we use the secondary image. So when you are using the SEM, there would be a selector switch, whether you should be using your backscattered detector or whether you should be using your secondary detector. Most of you would have done that. So by a judicious selection, you can investigate the features of the topography and surface relief. At the same time, when you switch on to the other mode, in the backscattered one, you will get some information related to the distribution of these species over this surface. Okay, I'm not going to details of all these things because there's not much time left. You can use this very same equipment to get identification of chemical species also. That is because when these electrons, the incident electron beam, it impinges on the surface, it would give rise to characteristic X-rays. Now, when these X-rays are energy analyzed, you would get information related to their chemical nature also, similar to how we used such an information for our XPS case. In the case of XPS, they were from our electrons which got emanated, but in this case they are X-rays. But the problem with this is that the resolution of those areas that you are trying to find, when that you are trying to differentiate in terms of elements, are much less. The reason being this, that is, when a narrow beam it enters into this matrix, X-rays would emanate from a very large volume, because those electrons which manage to enter into this would penetrate into very large volumes, and then X-ray emission would happen even from a volume which is slightly larger than that. And this is called as a sampling volume, which is slightly more than the interaction volume between the electrons and the particles of your matrix. And this sampling volume is roughly about 1 micrometer cubed. So therefore, if you are trying to differentiate between two elements, two different zones from your matrix, then at least they should be of reasonable size. Reasonable in the sense, you cannot achieve a resolution which is better than this 1 micrometer cubed when you are trying to identify elements using your So this is about SEM. I'm not going to the details of this. I'm going to show you an SEM images from experiments which are published in another source, which shows these top figures are where we got very large amount of friction, whereas those bottom figures, bottom SEM images, are those cases from we got slightly lower values of friction. So your SEM images are indicative of the amount of surface damage, and then that is getting correlated with your resistance to motion, because there is very large scale deformation and plasticity which is happening in the cases which are shown above on the top figures as compared to this. So you can exploit these features from your SEM to substantiate your results that you have found from your tribological experiments using a pin-on disc, a sliding experiment from a what you can say, fast oscillating machine and things like that, or even your 4-ball tester. Okay. Now the last one is from infrared spectroscopy. I'll try to finish it in 5 minutes. Suppose if you want to identify functional group from your surfaces, that means this is mostly used for tribochemical films involving organic compounds. You can use this spectroscopy. That is, when they are subjected to infrared radiation, your molecules would absorb energy corresponding to certain frequencies depending upon the different molecular fragments. Say, for example, if your surface it has an ester, then it would show some kind of an absorption which could be different when you don't have an ester. So that differentiation you can make use of by using this infrared spectroscopy. The equipment is like this. When the surface is subjected to, that means you have to load your sample into this particular machine, your film, your piece from your pin-on disc machine. Say you have cut a portion from your disc, from your pin-on disc machine, made it thin slice, put it into this machine, subject it to infrared rays using something which is called as a grazing angle IR method. That means it has to go. It is not like a liquid IR system where there will be a transmission through this, but it will graze your surface, and then this rays after grazing your surface would reach the detector, showing those signs of absorptions which have happened. I'm not going to the details of this because there is not much time left. I will share this PDF slides as PDF, which I think will be useful for those people who would find it useful. So what is important is that you get some information related to this in the form of this spectrum. This will show presence or absence of several different functional groups from this. Say, for example, I would look at one particular case, an ester. Yeah, the one which is below here, it shows an ester. So an ester is characterized by a C double bonded O formation. So if there is a C double bonded O fragment in your surface film, then this spectrum from your IR will show a peak which is close to 1710, 1725 wavelength, which is in the units of centimeter raised to -1. And then if it is an ester, to confirm it, you will see two more peaks, one which is corresponding to 1056 centimeter inverse and the other one corresponding to 1250 centimeters inverse. So you can use IR also to get useful information related to the chemical nature of your surface in terms of their functional groups. So all these characterization methods are, they have to work in conjunction. You have to use them together. No single method will give you a complete answer to what you are trying to find. You have to adopt a variety of characterization methods, perhaps two, sometimes five, or sometimes four or even more, to establish that cause and effect relationship. Say, for example, you cannot just afford to rely on your FTIR alone, because FTIR will give you information about your functional groups, but that alone may not be sufficient. It doesn't give you a coordination between, I mean, at least the infrared spectroscopy that I am trying to give you, it won't give you that information related to CL bonding. In that case, you will have to resort to your XPS. So you have to use a variety of characterization methods to arrive at these results. And then I am going to present one result from my IR experiment, which has got published in another paper, another journal, which shows the IR information from two different films. One which is lubricious and the other one which is less lubricious. It has become lubricious because we have used an ester. And from that, the IR information from that lubricious film, it shows a conspicuous peak close to 1710, which is indicative of that C double bonded O formation because of the presence of the ester which we had used, while the other one, it doesn't show. There is no peak corresponding to the C double bonded O formation. And then I have shown one figure which is below, which says that, or which is to tell that you may use your IR experiments for quantitative analysis also. You can use this information to relate it to the amount of the species which has got absorbed or adsorbed, not absorbed, adsorbed, when you subject your system to operate for a longer period or a shorter period. So this would complete our webinar. So let me just summarize this. So to establish the cause and effect relationship in tribology, we need to characterize the physical and chemical interfaces. XPS proves to be a powerful tool for chemical characterization. FTIR can be used to characterize functional groups in the organic films. Profilometric methods can be used to characterize surface. I could not really explain all which got included because the time was not sufficient. I had some 62, I don't know, around 60 slides. I've tried to describe them in the best possible way that I can. Try to discuss them in a way which will be of use for young researchers, because these are all meant for, not for the experts, because they are already aware of it. So they should get some useful information from this. So that is the value addition I expect being a part of this webinar. Thank you.
Thank you, sir. Thank you very much for your valuable and informative lecture on surface characterization. Hope almost all participants might have received good information from this talk. So definitely it would help these participants in enhancing their research activities.
Yeah.
Thank you very much, sir.
Okay.
And we have a few questions from Professor Radhakrishnan, sir.
Okay.
I'll conduct him so that he can straight away ask questions to you.
Okay, sir.
Professor Radhakrishnan, are you there, sir?
Yeah, I'm there. Can you hear me?
Yes,
Yes,
sir.
sir,
It is
I can hear
audible,
you,
sir.
sir. Yeah.
Yeah, thank you.
You may please express your question, sir, please.
Yeah, one question which I have is whether we can use a beautiful description of spintronics. I am actually a cardiac surgeon, I'm not an engineer.
Okay.
My doubt is whether we can use this spintronics concept to have low power electronics, which can take advantage of magnetic based devices and electric field writing. That is one thing. And second thing is whether we can use magnetic sensors which have slightly higher sensitive capacity for our newer diagnostic aids, medical diagnostic aids.
Okay. Okay. So there are two questions. I'm not an expert to answer
Yeah,
the second part, sir. Because
yeah.
I'm basically a tribologist, so I cannot really answer that part.
No,
Yeah. But the first one, definitely yes.
I'm actually impressed by, yeah, I am really impressed by what we can share as interdisciplinary utilization of this knowledge. What I was
Okay.
thinking is that if you have something like a larger VCMA coefficient and you have development of multiferroic material like what you said, we
Yes.
can have low power electronic circuits into medical devices. That is what I was thinking of.
Okay, fine. I mean,
Can it?
I mean,
Yeah,
your idea could be fantastic, sir. What I am trying
yeah.
to say is that I am not an expert to comment on that. That's what I meant.
Okay, okay.
I
And there
can,
was one interesting thing in your SPECT description also, because in cardiac SPECT, we are using SPECT for myocardial perfusion scanning. And recently we had zinc telluride being used for getting high resolution, low dose nuclear scans.
okay,
And so extended applications like using of a WBR software programs
okay,
actually can reduce the time for acquisition of these images and give better images also.
okay, sir.
So we have a lot of use of this into our cardiac imaging, especially nuclear medical imaging.
Okay,
We have a lot of use of this PET over PET.
okay, sir. Okay. Okay. So you should be basically coordinating, or you should be associating with material science experts, especially in the area of characterization.
Yeah, actually,
And
Geetam has stimulated me to
yeah,
develop
yeah.
one of a challenging.
May I know from which institute you belong to, sir?
Yeah, I belong basically to All India Institute of Medical Sciences. Right now, I'm working in Geetam as the cardiac surgery head, and I'm actually planning a device on total artificial heart.
Okay.
And I am extending my search into all these areas because I'm trying to develop fully implantable heart, which is very optimal use of electrical circuits and power and good biocompatible materials with less hemolysis also. Something which is one of a kind in the world so far. So that is why I'm digging into all these areas, and it's a beauty that you have brought about these concepts as an international webinar and seminar, and so many spin-offs from your talk can be used by me in my medical device also.
It was
Thank you so
great talk.
much for
Okay,
the
sir.
talk.
I mean,
Yeah,
it's great that, like we have listeners from institutes like All India Institute of Medical Science. It's simply great. Fine. If it was of use to you, then I feel, like I'm very happy about it. I can suggest one expert for you, sir.
yeah,
He was my professor at Indian Institute of Science, Professor
yeah.
Vikram Jairam.
Vikram Jaram.
Yes,
Okay.
Professor Vikram Jairam, Indian Institute of Science, Bangalore, who
Okay.
taught materials characterization for us when
Oh,
I did my
wonderful.
PhD
Yeah.
at ISU. He's a real expert in this area. In
Okay.
fact, one of those experts in this whole world, I would say. Professor would
Yeah.
be the ideal person, is a contact person, ideal person whom you can contact,
Yeah.
Like Professor is really wonderful.
Yeah,
Please
I
do
will actually
contact him.
share my email through Rajshekhar to you,
Yeah,
and
yeah.
possibly I can get in touch with him. I am actually connected with Indian Institute of Science also for some of my personal projects.
Okay,
So
sir.
maybe next visit I can meet him also in person.
Please, get an appointment, fix up an appointment with him.
Yeah.
Professor Vijay is known as Professor Vijay, would be
Okay.
the ideal person to help you, associate with you, advise you on all those important issues, sir.
Thank you. It was really a pleasure listening to you. Well covered.
It's my pleasure, doctor. It's my
Yeah.
pleasure.
Yeah. Thank you.
Thank you, sir. Thank you.
Thank you, sir. Professor Radhakrishnan, sir. It was an excellent. You're focusing on the work. So definitely, if you have any queries and all, to be reached to Professor Anirudhan. So please kindly mail me, sir. I'll forward that to Anirudhan, sir.
Sure.
Thank you very much, sir. Thank you very much for your participation.
Thank you so much.
Thank you, sir. So once again, on behalf of Geetham University Management and Geetham School of Technology from Bangalore, I would like to convey my heartfelt gratitudes to Professor Anirudhan for giving an informative lecture on surface characterization. So we wonder, like people from not only from the engineering background and people from medical background, like Professor Radhakrishnan, have shown their curiosity to participate in this and getting some information which would help them a lot in their research areas. Thank you very much, sir. Thanks a lot. One second,
Rajshekhar. My
Please,
vote
sir.
of thanks. My vote of thanks to you, Ashok, and Geetham.
Thank you, sir.
And then please, whenever Dr. Rajshekhar contacts you, let me have his mail ID so that in future, if I want some communication with him, it will be easy for me as well as Professor Radhakrishnan.
Definitely, sir. Definitely, sir.
Thanks. Thank you all for...
I'll contact with Radhakrishnan, sir. I'll get if any information or anything is there. I'll definitely forward you, sir.
Okay. So
Thank
you, viewers. Thanks for your patient viewing, your listening. Thanks very much. See you.
Thank you, sir. Thank you very much. Thanks a lot, sir. Bye-bye, sir.
Thanks, gentlemen.
You have to say thank you.
Bye-bye. Shall I leave?
Okay, sir. You can, sir.
Thank you.
Thank you.
I request all participants to just fill the feedback form has already been posted on a group. And at the same time, nothing to worry about your attendance and all. We will look after, and every participant would be getting a certificate online. E-certificate would be mailed to them after the completion of this 5-day workshop. And I also thank each and every participant. I thank you one and all. Thank you very much. I'll end the session. Thank you.